In the darkest reaches of space, the earliest universe begins to look denser and brighter than anyone expected. Ultra-early galaxies glow sooner. Massive black holes grow faster. And a quiet mismatch in cosmic expansion, the Hubble tension starts to feel like a clue instead of a glitch. Tonight's journey drifts through ancient afterglow, faint speckled patterns and the slow physics that turns tiny ripples into vast structure. If this calm science story helps, please tap like, subscribe for more long-form sleep documentaries, and turn on notifications so the next cosmic night arrives right on time. A deep infrared sky appears as a dark basin sprinkled with quiet sparks. The early universe looks denser and brighter than predicted, and that simple mismatch reshapes what formation and expansion should look like. In that basin, the faint points do not spread evenly. Some gather into compact knots with steep brightness gradients. Some smear into soft ovals with dim halos. A few stretch into thin arcs as if space itself pulls their light into curved threads. The scene carries a calm surprise. The surprise is not a single rare object. The surprise is the crowd. A wide survey finds about 10 times more bright, very early galaxies than older expectations. It resembles walking along a riverbed, where polished stones appear in every step, not in scattered pockets. The extra stones do not demand a new river. They demand a new account of how quickly stones gather. A first payoff arrives quietly. If so many bright systems exist so early, then the early universe is not a sparse preface. It's already a busy chapter with structure and contrast. In that region, brightness is not only a glow, it is a map of density. Light arrives with different shades of infrared. Some sources look warm and long in wavelength. Some look less stretched and more compact. That variety forms a timeline laid across one frame. The frame is still, yet it contains many ages at once. A second visual anchor settles in. The image resembles frost crystals on a pond at dawn. Clear areas remain dark. Dense areas whiten into clustered patterns. The patterns suggest filaments and gaps. The gaps feel as important as the knots. The scale shift is gentle. The view moves from a single faint smudge to a web that spans enormous distances. The web is not drawn with lines. It is implied by where the smudges refuse to be. The first concept is cosmic stretching. Expansion lengthens light waves while they travel. A longer wave arrives redder in infrared. Redshift is the name for this stretching. Redshift is a measure of how much a wave is lengthened. Like a slow swell on a lake, the same wave becomes longer as the surface grows. The meaning is immediate. Greater stretching points to earlier emission and greater distance. A payoff follows. The colour of a faint dot becomes a clock hand. It does not mark a date with certainty. It marks an era, yet the clock hand must be read with care. Some dots look red for another reason. Dust can absorb short wavelength light. Dust can re-emit energy as longer infrared glow. A dusty system can mimic extreme distance. In that region, two effects overlap. One is stretching by expansion, one is reshaping by dust. The second concept is number density. Density here does not mean pressure. It means how many luminous sources occupy a slice of volume. In a given patch of sky, more sources imply more early structure. They also imply faster assembly. A calm analogy holds the idea. A winter field can look empty from far away. A closer look can reveal many seed heads beneath the snow crust. The crust hides abundance. Infrared reveals what shorter wavelengths miss. The payoff arrives again. If abundance appears where emptiness was expected, then the earliest assembly may be more efficient. Efficiency is not a moral word. It is a rate. Gas cools and collapses faster. Stars ignite sooner. Compact systems build up light rapidly. A physical detail sharpens the picture. Many early galaxies appear small in size. Their light concentrates into tight cores. The outer edges fall off quickly. A bright center sits inside a fainter envelope. That envelope can show a smooth gradient. Sometimes it shows clumps like beads on a thread. Those shapes matter. They hint at rapid formation inside dense regions. They also hint at interactions. Even in youth gravity can pull structures into elongated forms. Another visual anchor appears. A thin band of clouds can be seen from above. The band breaks into lumpy segments. Between segments, dark lanes remain. The early sky shows a similar rhythm. Bright islands separated by the quiet gaps. The third concept enters softly. Two ways of estimating expansion disagree. This disagreement is called the Hubble tension. One method ties expansion to the afterglow of the early universe. Another method ties expansion to nearer distance markers. Both methods are precise in their own domains, yet the answers do not match. The mismatch is not a small rounding difference. It is large enough to persist through repeated checks. The early universe being denser and brighter does not solve this tension by itself. It adds pressure to every assumption that connects early conditions to later expansion. A payoff arrives in the form of a question answered. Why does early brightness matter to expansion? It matters because models of expansion rely on a consistent story of how structure grows. If structure grows faster, then the mapping between early patterns and later distances may shift. The story does not break with noise. It breaks with quiet accumulation. More early light means more early mass turned into stars or energetic cores. That can alter how distances are inferred from light. It can also alter how the early Webb seeds later flow. Another scale shift follows. The mind moves from a compact galaxy core to the full span of time between early glow and present measurement. It is like watching a river from its headwaters to its wide delta. Small changes upstream can change the branching downstream. Yet the river cannot be watched continuously. The early universe offers only snapshots. That is where the limit of observation appears. At extreme distance, faint sources blur together. Two close objects can merge into one point. A small galaxy beside a bright core can be mistaken for a single system. Color can be skewed by dust. Brightness can be boosted by gravitational lensing. Lensing bends light and can magnify a background source. It can also distort shape into arcs or partial rings. The limit is specific. It is the limit of resolution and the limit of interpretation from a single frame. Some quantities require spectra. Spectra spread light into wavelengths and reveal sharp features. Those features can anchor distance, yet the features are faint in the earliest objects. Noise can mimic a line. A line can hide under a sky background. The safest inference is often broad and order of magnitude. That safety is not a weakness. It is a disciplined calm. Another visual anchor lands slowly. A distant mountain range at dusk can look like one smooth silhouette. As darkness deepens, separate ridges merge into one shape. Only with clearer air do the individual peaks emerge. The early sky has similar ambiguity. Peaks and ridges can blend. A quiet payoff follows. The brightness excess may be partly real and partly a mirage from selection and blending. Even that mixed answer changes the story. It means the early universe is close to the limits of inference. It also means that any firm conclusion must survive multiple checks. The promise of the arc becomes clear with our emphasis. The script will follow three threads. The first thread is the stretching of light as the timekeeper. The second thread is the early crowd of luminous systems and what makes them so bright. The third thread is the stubborn mismatch in expansion estimates and what early conditions imply for it. The tone stays gentle. The conclusion is not a sudden twist. It is a gradual sharpening of what the first images already suggest. In the next section, the quiet mechanics of stretched light sets a more stable clock. The same deep field begins to feel less like a picture and more like a timeline. In that dark basin of infrared color shifts, feel like slow music changing key. Light behaves as a traveling wave that is stretched by expansion, and that stretching becomes the calm clock used to place the earliest galaxies. A single point of light begins as a tight ripple at emission. The ripple has a rhythm. It carries a wavelength like a measured spacing between crests. Over immense travel the spacing grows. The crests separate. The ripple arrives longer and softer. This stretching is redshift. Redshift is how much light is stretched by expansion. A payoff arrives quickly. If stretching can be read, then distance and time can be read together. The reading is not perfect. Yet it is the most stable bridge between a faint image and a cosmic era. A primary visual anchor forms. A long ribbon of silk drifts through still water. At first, the weave looks tight. Farther along, the same weave looks looser because the ribbon has been gently pulled. The pattern is the same. The spacing changes. The change carries information without needing extra decoration. Redshift works in a similar way. The pattern of light remains. The spacing shifts. A main number grounds the idea. A typical wavelength can be stretched by about a factor of 10 for the earliest visible galaxies, like a 10-step staircase, becoming 100 steps with the same rise repeated. The comparison is simple. The meaning is deep. A larger stretch means a longer journey through expansion. The scale shift follows. A single ripple spans a fraction of a second in its local source. That same ripple then rides for billions of years before arriving. The ripple does not age. The universe around it expands. The wave records that growth. A second payoff arrives. When early galaxies seem too bright, the first check is whether distance is right. If distance is wrong, brightness is misread. If distance is right, brightness becomes a genuine challenge. A second visual anchor appears smaller and calmer. A thin fog layer lies above a lake at dawn. A lamp on the far shore looks dim. A lamp on the near shore looks bright, yet fog thickness can fool the eye. Distance and obscuration can trade places. In cosmic light, dust can play the role of fog. It absorbs short wavelength light. It re-emits at longer infrared wavelengths. That effect can imitate extreme stretching. Two concepts now sit side by side. One is redshift from expansion. One is reddening from dust. They can look similar in simple colours. The difference lies in fine structure. A spectrum can separate them. A spectrum spreads light into wavelengths. It reveals features that shift in a consistent way with expansion. Some features are sharp edges, some are narrow peaks. The details act like notches on a ruler. A payoff arrives again. With spectral features, distance becomes more than a guess. It becomes a measured placement on the timeline. A physical detail helps the mind hold the mechanism. In a spectrum, a steep drop can mark an absorption boundary. The boundary slides toward longer wavelengths with distance. The edge remains steep. The edge is like a cliff line on a coastline map. Its position changes. Its shape stays. That stability is a gift. It allows faint systems to be sorted by era even when images are blurred. Another scale shift arrives. The mind moves from a boundary in a spectrum, which is a tiny change in wavelength, to a change in cosmic age measured in hundreds of millions of years. The bridge between these scales feels unreal at first, yet it is built from consistent physics. Light carries the ruler, expansion moves the markings, the section reaches its limit of observation quietly. At extreme faintness, spectra become noisy. A weak feature can vanish into the background. A false feature can appear from random fluctuations. The limit is specific. It is the limit of signal to noise and the limit of spectral resolution. If resolution is too low, multiple features blend into one broad bump. If noise is too high, the cliff edge becomes a slope. Then distance becomes uncertain. Uncertainty spreads outward. Brightness and size are misestimated. Number density can be biased. A payoff follows small and steady. Because of these limits, safe conclusions often use broad categories rather than precise values. A galaxy is placed as very early rather than pinned to an exact moment. A population is counted with careful corrections rather than treated as a raw tally. The caution does not slow discovery. It makes discovery durable. A third visual anchor arrives. Snow falls onto a dark cloth. A few flakes are sharp and bright. Many are faint and half melted. Counting only the sharp flakes misses most of the fall. Counting every blur risks counting shadows. The best count balances both. Cosmic surveys face an equivalent balance. Another physical detail returns to the image plane. Some early sources show compact cores with soft skirts. Some show elongated smears. Some show partial arcs. These shapes matter because lensing can magnify and distort. A foreground mass can bend light. It can stretch a background source into a curved segment. It can brighten it without changing intrinsic power. The concept is not a complication for its own sake. It's a necessary filter. Another payoff lands. If lensing boosts brightness, then the true brightness distribution may be lower. If lensing is rare, then the brightness excess is more intrinsic. Either outcome still informs early structure. The tone remains gentle. The next section moves from the clock to the crowd. It looks at what denser and brighter means in physical density and light production. It does so without haste. A field of early light can feel quiet until the brightness starts to pile up in the same small places. In that region, denser and brighter means more luminous sources per volume and more light packed into smaller shapes. The first change is density. More early galaxies appear in a given slice of space than older expectations allow. The second change is brightness. Many of those galaxies look too radiant for their youth. A calm payoff arrives. If both changes hold, then early structure is not only present, it is already efficient at turning cold gas into light. A primary visual anchor settles into view. A dark pool holds a single drop of ink. The drop sinks and forms a tight core. A faint veil fans outward as a smooth gradient. The core stays sharp, the veil stays soft. The image resembles an early galaxy with a bright center and a dimmer skirt. The physical detail matters. The steep fall in brightness from center to edge suggests compact formation. It suggests dense regions where material gathers quickly. A simple number anchors the scale. Some ultra-early galaxies appear about 3,000 light-years across, like a small pond, compared to a wide sea of starlight. The comparison holds the feeling of compactness without strain. The scale shift follows gently. 3,000 light-years is vast in ordinary terms, yet it is small against a mature spiral galaxy. The mind moves from a compact core to a cosmic population. Many such cores appear in the same early era. That abundance shapes the meaning of brightness. Brightness is not only how much light arrives. Brightness is also how that light is distributed across an image. Surface brightness is the phrase used for this. Surface brightness is light per apparent area on the skybane. A compact object can appear more intense because its light is concentrated. A payoff arrives again. A smaller size can make a young galaxy look more impressive without requiring extreme total power. Yet the picture refuses to become easy. Even after accounting for size, many early objects still look unusually luminous. Two possibilities sit side by side. One is genuine high production of starlight. The other is a selection effect. A survey sees the brightest things first. It can miss faint extended objects. The limit of observation appears here with precision. The limit is a surface brightness threshold and a finite blur in the image. Faint outskirts can fall below detection. Small neighbours can blend into one brighter blob. At extreme distances, the blur can merge two compact sources into one. The merged source looks denser and brighter than either alone. A calm visual anchor returns in a new form. A thin layer of mist lies on black stone. Only the thickest droplets catch light. The finer film remains nearly invisible. The stone seems dotted rather than evenly wet. The same bias can occur in a deep field. The brightest compact knots stand out. The faint diffuse glow can remain hidden. A payoff settles in. Even if some brightness excess is selection, the density of detectable compact sources still signals early structure. It implies that some regions reach high contrast quickly. That contrast means gravity has already carved valleys and ridges in density. The next concept enters softly. Brightness can spike if star formation happens in bursts. A burst is a short, intense period of star formation. Like a dry sponge suddenly dipping into dye, a gas cloud can rapidly brighten when conditions align. The dye image holds the idea. The sponge does not change its identity. It changes its saturation. A galaxy can do the same. It can spend much time faint. It can spend short intervals bright. If many galaxies are caught during bright intervals, the sky appears more luminous than an average would suggest. A payoff follows. The density of bright detections can increase even if the underlying population is large and mostly dim. This makes early brightness a question of timing. It also makes brightness a question of duty cycle. Duty cycle is the fraction of time a source stays bright. Duty cycle is the time spent in a bright state. A short duty cycle can still produce many bright detections if the population is large. The scale shift arrives again. A burst can last a few million years. The travel time of the light is billions of years. A brief flare becomes a long-lived point on an image. The image holds many brief moments at once. That stacking of moments can mislead intuition. The eye sees a stable field. The physics contains flicker. Another physical detail grounds the flicker. In compact galaxies, gas can form a dense central disk. The disk can show a gradient from hot inner zones to cooler outer zones. The gradient can concentrate ultraviolet light in the center. Dust and gas around the center can scatter and absorb. The absorbed energy can reappear as infrared glow. The glow can smooth over clumps and make the core look like a warm bead. A calm payoff lands. Even without invoking exotic physics, compactness bursts and obscuration can combine to make early systems look surprisingly bright. Yet the story still carries tension. Some objects remain too bright even after these effects are considered. That persistence matters. It keeps the door open for changes in the early recipe. The recipe can change in several gentle ways. Gas might cool faster in dense regions. Fragmentation might favor different stellar masses. Energetic cores might contribute more light than expected. Those possibilities do not need to be claimed as fact. They need to be treated as hypotheses with checks. The limit of intuition appears beside the limit of observation. Intuition expects slow assembly because mature structure looks orderly. Intuition expects youth to be sparse because later eras feel more crowded. Both expectations can fail because gravity grows structure faster in denser conditions. Both expectations can fail because observation favors the highest contrast knots. The mind must accept that a bright compact dot can hide many unseen components. It can hide faint companions. It can hide extended halos below threshold. It can hide lensing magnification from an intervening mass. Lensing does not create light. It redistributes and amplifies it. Lensing can pull a source into an arc. It can create a partial ring. It can also leave shapes that look only slightly stretched. The limit is specific. Without clear distortions, mild magnification can be hard to identify. That uncertainty affects luminosity estimates. Another visual anchor arrives. A pebble dropped into still water makes concentric rings. If a shallow ridge lies beneath the surface, the rings distort and bunch on one side. The pattern changes without adding new ripples. Lensing acts like the hidden ridge. It reshapes the pattern of light. A payoff follows. If some of the brightest early sources are modestly magnified, then the intrinsic brightness excess shrinks. If not, then the excess points back to early physics. Either way, the dense early census remains meaningful. It shows that many luminous systems are present near the dawn of galaxies. The arc of the script remains calm. The next section moves from brightness to confirmation. It follows how distance is pinned down for the most extreme candidates. It tracks how a faint feature becomes a secure placement on the timeline. It does so with a steady breath and a soft pace. A distant glow becomes trustworthy only when its light shows a distinct edge. A signal would be placed in the early universe when a spectral boundary slides to longer wavelengths in a consistent way. The boundary is not a decoration. It is a physical mark made by atoms and the intergalactic medium. It appears as a sharp drop in intensity across a narrow range of wavelengths. In an ideal case, the drop looks like a clean cliff. One side stays brighter. The other side falls quickly. That shape is a calm anchor. A payoff arrives early. When the cliff is found, distance stops being a guess from colour alone. It becomes a measured shift. The primary visual anchor forms. A calm shoreline lies under moonlight. A line of wet sand marks where the tide has reached. The wet band ends in a crisp edge. Past the edge, sand stays pale and dry. The tide line does not explain the whole ocean. It confirms that water has been there. The spectral edge works the same way. It confirms that light has travelled through a specific early environment. It confirms a placement on the cosmic timeline. At this distance, the details are delicate. The source is faint. The background is not empty. A broad glow from the sky can wash out weak structure. Random fluctuations can mimic a step. A true step can be softened into a slope. The section moves through a checkpoint. First, an image suggests extreme distance because the source looks very red in infrared. Next, a spectrum is needed to confirm whether the redness is stretching or dust. The spectrum spreads the light into fine bins. It reveals whether the steep edge exists. It reveals whether multiple features line up in the same shift. A payoff arrives again. One feature alone can mislead. Several agreeing features make the placement resilient. A main number anchors the sense of scale. The most extreme candidates can sit within about 500 million years of the beginning, like the first few minutes of a long night where dawn still feels far away. The comparison keeps the timescale gentle. It also carries weight. 500 million years is long in ordinary life. It is short in cosmic history. The scale shift follows softly. A small shift in wavelength barely perceptible in a plot corresponds to a vast shift in age. The mind holds a tiny edge. The mind then holds an era when galaxies first assemble. The next checkpoint brings in the intergalactic medium. Between galaxies, gas is not evenly transparent. In very early times, much of that gas is neutral. Neutral gas absorbs certain ultraviolet wavelengths. It creates a boundary in the spectrum. This boundary is often called a break. Break is a sharp drop caused by absorption. The definition is brief and clear. The everyday analogy follows. A thin curtain can block a bright lamp. The lamp still shines. The curtain removes part of the light. What remains is a dimmer, redder glow. The importance follows. The curtain reveals the state of the space between galaxies. It also helps confirm distance. A physical detail returns to the edge itself. The drop can be steep. The steepness depends on both the source and the intervening gas. A source with strong emission can show a partial recovery just redward of the edge. That recovery can look like a small bump. The bump is not a story device. It is a diagnostic. It suggests energetic processes in the source. It suggests ionized pockets around it. A payoff settles in. Even a faint bump can separate a true early galaxy from a dusty nearer imposter. Another visual anchor appears secondary and quiet. A thin film of ice covers a puddle. A crack forms a line where the ice thickness changes. Light reflects strongly on one side and softly on the other. The line is real, yet it can be blurred by ripples beneath. In spectra, noise plays the role of ripples. Noise can smear the line. The limit of observation now enters with precision. The limit is spectral resolution and signal to noise. If resolution is too low, a sharp edge becomes a gentle slope. If noise is high, the slope can look like random variation. Confirmation then depends on repeatability and consistency. Multiple exposures can reduce random noise. Yet time is finite. The faintest sources cannot be measured forever. Another limit follows. The measured spectrum can be contaminated by nearby objects. Two sources can overlap in the same aperture. The combined light can produce a false edge. It can also hide a true one. The payoff arrives in a calm safeguard. Confirmation is strongest when the edge position matches other independent indicators. Those indicators can be additional lines. They can be consistent photometric colors across multiple bands. They can be a lensing model that predicts magnification and distortion. The section stays within its concept limit while keeping the journey moving. Redshift is already known. The new focus is the spectral break and the intergalactic medium. Together they provide a stable placement. A scale shift arrives again. The boundary is caused by atoms responding to ultraviolet photons. That interaction happens on microscopic scales, yet the imprint spans cosmic volumes. It is made by countless atoms across vast distances. The same physics that shapes a laboratory absorption edge shapes a cosmological one. A payoff lands softly. This is why early confirmation feels reliable. It is not based on one exotic assumption. It is based on simple absorption repeated many times. The section returns to the larger arc. Verified extreme distances tighten the tension with models. If many sources are truly that early, then formation proceeds rapidly. If only a few are truly that early, then selection and dust dominate. Either answer is useful. Verification also affects the Hubble tension indirectly. Early distances set expectations for the growth of structure. Growth of structure feeds into the interpretation of the early background and later distances. Nothing is forced. The links are gentle but real. Another physical detail grounds the closing. Some confirmed early galaxies show compact cores with a smooth radial gradient. Some show slight elongation. Some show faint companions that sit just outside the core. The companions blur into the background unless carefully separated. This reminds the mind of the observation limit again. The next section transitions into dust and hidden light. Dust complicates the color clock. Dust also reveals energetic processes that make early systems brighter than expected. The shift forward is calm, the shoreline line remains, the tide of interpretation moves on. A faint object can look quiet until dust changes the color of its light. Light behaves as a messenger that can be absorbed and re-emitted, and dust turns that detour into infrared brightness without needing extreme distance. The first concept is dust itself. Dust is tiny solid grains mixed with gas. Dust is small enough to float with gas flows. Dust is large enough to block and scatter short wavelength light. A compact early galaxy can hold dust in layers. The inner region can be dense, the outer region can be thinner. This layering creates a physical gradient. The center can look redder, the edge can look bluer, the shape can show a warm core with a cooler skirt. A payoff arrives early. If dust is present, then redness does not always mean greater stretching by expansion. Redness can mean that blue light has been removed. Dust does not destroy energy, it shifts it. Absorbed energy warms the grains. Warm grains re-emit in infrared. The re-emission is softer and broader. It spreads over wavelengths rather than forming sharp lines. The primary visual anchor forms. A charcoal ember glows under a thin blanket of ash. The ash dims the sharp orange. The ember still warms the blanket. The blanket then glows faintly in a broader, softer way. The ember remains. The path of light changes. This is how dust can hide intense starlight and reveal heat instead. A main number grounds the intuition. Dust grains can be about 1/10 of a micron in size, like a film far thinner than a soap bubble. The comparison holds the smallness without strain. The scale shift follows. A grain smaller than a common cell can change the appearance of an entire galaxy. Countless grains spread across thousands of light years reshape a spectrum. The second concept is attenuation. Attenuation is light loss by absorption and scattering. The definition stays short. 2 everyday sentences follow. A beam through fog looks dim and red. The fog does not glow strongly in visible light. The fog still changes what reaches the eye. Dust acts like fog for starlight. The importance follows. Attenuation can make a nearby dusty object mimic a distant clean one in simple color. This is why confirmation needs more than a single image. A payoff arrives again. Once dust is considered, some early brightness tension can soften. A galaxy can be intrinsically bright yet look less bright in visible bands. The missing visible light can reappear as infrared glow. This can raise the total energy output without making the object look sharp and blue. In that region, infrared brightness becomes a clue. It can signal hidden star formation. It can also signal energetic cores. The section stays calm and selective. The third concept is thermal emission. Thermal emission is infrared light from warm dust. The definition is brief. 2 analogy sentences follow. A stone warmed by sunlight releases heat after sunset. The stone radiates gently without needing a flame. Dust does the same on microscopic scales. The importance follows. Thermal emission can carry the energy budget of a galaxy, even when visible light is muted. Another visual anchor appears. A thin veil of smoke drifts above a candle flame. The flame flickers sharply. The smoke softens the flicker. The smoke itself becomes faintly luminous near the flame. In early galaxies, dust plays the role of smoke. The dust blurs and reddens. The dust also glows. A physical detail sharpens the scene. The central region can show a smooth warm gradient. It can also show patchy lanes where dust is thicker. These lanes can create irregular edges. They can carve dark notches through a bright core. In infrared, the notches can soften into less contrast. The core can become more rounded. The skirt can become more apparent. A payoff arrives. Morphology changes with wavelength. What looks compact in one band can look extended in another. That difference helps separate dust effects from pure distance effects. The limit of observation enters with precision. The limit is degeneracy between dust and redshift when only broad colours are available. A very dusty galaxy at moderate distance can resemble a less dusty galaxy at extreme distance. The limit is also finite wavelength coverage. If observations sample only a few bands, the shape of the spectrum is underconstrained. Noise can push colours redder or bluer. The result can scatter objects into the wrong bin. A calm payoff follows. This is why populations are described with ranges and probabilities rather than absolute lists. Confirmation relies on spectral edges and multiple features. Dust effects are inferred from the smoothness and curvature of the spectrum. Another limit appears. Dust temperature is not measured directly from a single point. Temperature is inferred from the peak and slope of infrared emission. With sparse data, the inferred peak can shift. Then the energy budget can be overestimated or underestimated. The section returns to scale shift. Dust heating occurs as photons are absorbed. That is a process on timescales shorter than a second for a grain. The emitted infrared photon then begins a journey of billions of years. A fast microscopic exchange becomes a slow cosmological message. Another visual anchor settles. A raindrop strikes a calm pond. The splash is instant. The ripples travel outward long after. Dust heating is the splash, infrared travel is the ripple. A payoff arrives again. If the early universe is denser, then dust can form earlier than expected. Dust requires heavy elements. Heavy elements require stars. If stars ignite quickly in dense regions, dust can appear quickly as well. This creates a feedback loop for appearance. Early galaxies can look redder and brighter in infrared. They can also hide much of their star formation from shorter wavelengths. This can inflate counts of infrared bright sources, while leaving fewer blue sources. The narrative stays balanced. Dust can explain some surprises. Dust cannot explain all. Some early sources show red colours without the curved spectrum expected from heavy dust. Some show strong features that point to extreme redshift. The next step is to use dust as a diagnostic rather than a loophole. Dust indicates rapid enrichment. Rapid enrichment indicates intense early star formation or energetic cores. That connects back to the brightness excess. It also connects forward to the question of fast-growing massive black holes. A gentle transition closes the section. The next section moves into compact central power sources and how accretion can produce light early. The story shifts from dust as a veil to the engines that can shine behind it. A compact red point can hide a powerful center behind a smooth infrared glow. In that region, a fast-growing massive black hole becomes plausible when gas forms a dense disk and converts gravity into light. The first concept is accretion. Accretion is gas falling inward and heating by friction. The definition stays short. Two analogy sentences follow. Water spiraling into a drain speeds up near the center. The speeding flow warms by rubbing and mixing. The importance follows. The same spiral can make a compact source shine intensely without needing many stars. A primary visual anchor forms. A dark whirlpool in a still pond shows a bright ring of foam. The ring is thin, the center is darker. The foam traces a boundary where speed and shear peak. In an accretion disk, a similar boundary exists. The disk is not a solid plate. It is layered gas. The inner region is hotter. The outer region is cooler. Between them, brightness changes as a gradient. A physical detail sharpens the picture. The disk can be thin and flat. It can also puff up into a thicker structure if cooling changes. A faint shroud of dust can sit farther out. The shroud can reprocess light and soften the spectrum into infrared. A payoff arrives early. If a compact disk dominates the light, then a galaxy can appear brighter than its stars would suggest. The second concept is a seed black hole. A seed is an initial black hole mass that later grows. Seed is the starting mass for later growth. The definition is brief. 2 analogy sentences follow. A small knot in a thread can become a larger tangle if fibers keep winding in. The knot does not need to be large at first. It needs steady winding. The importance follows. If seeds are larger than expected, growth constraints relax. A main number anchors the tension. Some early systems imply black holes near 1 billion solar masses, like a mountain rising where only low hills were expected. The comparison carries the shock without harshness. The scale shift follows gently. 1 billion solar masses is enormous, yet the light from that mass comes from a region far smaller than a galaxy. The engine is compact. The glow can travel billions of years. A brief surge in feeding becomes a steady point on an image. A payoff arrives again. Compact engines can explain bright early points without requiring every galaxy to be extreme. Only a fraction needs such engines. That fraction can still influence the census because engines are luminous. The third concept is the Eddington limit. The Eddington limit is when radiation pressure balances gravity. The definition stays within 12 words. 2 analogy sentences follow. A strong wind can push back falling dust. A stronger pull can still win if the wind is channeled. The importance follows. This limit suggests a typical growth speed, but special flows can bend it. The section stays careful. No claim is made that limits are broken everywhere. The point is that growth can be intermittent. Growth can be organized by the geometry. If gas arrives in a dense stream, radiation can escape in preferred directions. The disk can radiate away energy while still drawing in mass. Another physical detail grounds the mechanism. Close to the center, gas orbits rapidly. The shear heats the gas. The disk surface can be bright. The disk edge can fade smoothly. A shadowed lane can appear if a thicker inner structure blocks light. That shadow can imprint a dip in the spectrum. Dust farther out can absorb the highest energy light and re-emit in infrared. This creates a broad, warm hump rather than sharp lines. A visual anchor appears quiet and slow. A lantern behind a paper shade looks soft and red. The paper hides the sharp flame. Heat still passes through. The shade glows with a smooth gradient. In early galaxies, dust can be the shade. The engine is the lantern. The payoff follows. A red compact source can be powered by an engine even if the starlight is modest. This helps explain why some early galaxies appear too bright for their size. The limit of observation enters with precision. The limit is separating engine light from stellar light when only broad infrared colours are available. Both can look red, both can look compact. A spectrum can help, but spectra are faint. Another limit appears. Engine indicators can be subtle at extreme distance. Lines can be weak. Lines can blend. Noise can hide the shape. The inference then becomes indirect. It relies on energy distribution across bands. It relies on compactness and variability. Yet variability is hard to measure with sparse visits. The payoff arrives in a calm safeguard. A population approach can still work. If many compact red points share similar spectral curvature, then engines may be common. If only a few show that curvature, then engines are rare. Either result informs early growth. Another scale shift arrives. The disk is built from gas particles. Collisions and viscosity act on microscopic scales. The outward radiation field acts across light days. The surrounding galaxy acts across thousands of light years. The cosmic environment acts across millions of light years. A small engine sits inside a large scaffold. The scaffold supplies fuel by gravity. The engine returns energy that can heat and push gas outward. This feedback can shape early star formation. Feedback is energy from a central source altering surrounding gas. The definition is brief. 2 analogy sentences follow. A hot stone placed in cold water warms a thin layer first. The warmth then spreads and changes the flow. The importance follows. Early engines can regulate how quickly gas turns into stars. They can also affect dust by heating and dispersing it. A visual anchor returns in a new scene. A thin ring of mist forms around a warm spring in cold air. The ring marks a boundary where heat meets cold. In a young galaxy, a similar boundary can form where engine radiation meets denser gas. The boundary can appear as a bright inner region and a dimmer outer zone. The payoff lands softly. This boundary helps explain gradients seen in compact early sources. It also links engines to the broader claim of a brighter early universe. If engines are common, early luminosity rises. If engines are rare, early luminosity must come mostly from stars and bursts. The next section shifts to the pace of feeding. It explores how bursts of accretion can outpace steady growth without breaking into drama. The tone stays even. The bright ring of foam remains a quiet image as the flow continues forward. A bright compact core can look steady while its feeding happens in brief surges. In that region, fast black hole growth becomes plausible when accretion comes in bursts and the brightest phases dominate what is seen. The first concept is duty cycle. Duty cycle is the fraction of time spent bright. The definition stays short. 2 analogy sentences follow. A lighthouse rotates and flashes. Most moments are dark. A few moments are bright and memorable. The importance follows. A small fraction of time can shape the whole census because bright phases are easiest to detect. The primary visual anchor forms. A calm shoreline at night shows a distant beacon. The beam sweeps across the water. A thin line of light slides over small ripples. Each pass is brief, each pass is clear. The sea between passes remains dark. Accretion can act like that sweep. A black hole can spend long periods in modest inflow. It can enter short intervals of dense supply. During those intervals, the disk brightens. The infrared output rises. Dust around the core warms. The system appears as a compact red point with a smooth gradient. A payoff arrives early. If early engines flicker in this way, then many detected sources can represent a much larger hidden population. The second concept is super Eddington accretion. Super Eddington means accretion above a typical radiation balance. The definition stays within 12 words. 2 analogy sentences follow. A river normally spreads into a calm delta. A sudden storm can force water through a narrow channel faster. The importance follows. In special flows, radiation does not halt inflow as effectively as a simple picture suggests. The reason is geometry and trapping. A thick disk can form. Gas can puff into a funnel shape. Radiation can escape along lower density directions. Inflow can persist through denser lanes. A physical detail grounds the idea. A thick inner disk has a curved surface. It creates a shadowed equatorial zone. It creates a brighter polar region. The brightness pattern is not uniform. It has a gradient across angles. This can affect what is inferred from a single line of sight. Another payoff arrives. A system can look extremely bright without requiring perfectly isotropic emission. It can also look less bright if the brighter directions do not point toward the observer. This means the census can be biased in both directions. Bright phases are overcounted, dim phases are undercounted. Orientation adds another filter. The section keeps a calm pace through checkpoints. First, a seed grows by ordinary accretion during long quiet intervals. Next, dense streams arrive and trigger bursts. Then feedback from the burst heats surrounding gas and slows the next episode. The cycle repeats. The cycle need not be regular. It only needs to occur. A main number anchors the pace. A single burst can last about 1 million years, like a brief flare in a calendar where a long season is mostly quiet. The comparison keeps it gentle. The scale shift follows. 1 million years is long on human scales. It is short compared to cosmic travel time. Light from that burst can take billions of years to arrive. The burst becomes a static point on an image. Many static points can represent many separate brief episodes. A payoff lands softly. This is how fast growth can be hidden and inside a calm-looking deep field. The limit of intuition appears. Intuition expects steady growth like a slowly rising tide. Intuition expects averages to describe reality. In burst-driven systems, averages can be misleading. The average can be low while the important moments are high. The limit of observation appears next with precision. The limit is temporal sampling. With only a few observation windows, variability is hard to measure. A flickering source can look constant if it is caught at similar phases. A quiet phase can be missed entirely. Another limit is spectral ambiguity. A thick disk can produce a smooth continuum. Dust reprocessing can also produce a smooth continuum. Separating the two can require spectral lines that are faint at extreme distance. A payoff follows. Even without variability measurements, population statistics can still suggest bursts. If many compact sources cluster near the brightest end, then duty cycle effects and selection can be inferred. If the bright end is smooth and continuous, then steady models may fit better. Either path provides constraints. A secondary visual anchor appears. A patch of dry ground after rain shows dark channels where water briefly ran. The channels remain as faint grooves. The water is gone. The history is still visible. In early galaxies, bursts can leave lasting marks. Outflows can carve cavities. Radiation can ionize a bubble. Dust can be pushed into a shell. A physical detail sharpens this. A shell can appear as a faint ring-like structure around a compact core. The ring is not always resolved. It can show as a subtle shoulder in the brightness profile. It can also show as a slight flattening of the core gradient. A payoff arrives. Such shells can hint at episodic energy release. They also hint at feedback shaping the next supply. The section returns to the broader arc. If early black holes grow in bursts, then the implied growth time shortens. This helps reconcile early massive engines with the young age of the universe. It does not remove every tension. It shifts where the tension sits. The tension moves toward fuel supply. It moves toward seed formation. It moves toward how dense streams arise so early. Those topics remain gentle. They can be explored with safe order of magnitude reasoning. The limit of observation returns briefly. Fuel inflow is not seen directly at extreme distance. It is inferred from luminosity and spectral shape. Geometry complicates inference. Dust complicates inference. Lensing can complicate inference. The result is a range rather than a single number. A payoff settles. Range-based inference is still powerful when many sources are counted. The population can reveal whether bursts are required. The population can reveal whether duty cycle is small or large. The next section shifts from bursts to the curious class of compact red sources, sometimes called little red dots. The transition is calm. The beacon continues to sweep. The dark intervals remain. The bright intervals carry most of the information. A tiny red point can sit in a deep field like a quiet ember that refuses to fade. In that region, compact red sources become important because their colour size and abundance hint at either dense stellar cores or buried black hole engines. The first concept is compactness. Compactness is light confined to a small region. The definition stays short. Two analogy sentences follow. A drop of dye in water can remain tight if the water is still. If the water stirs, the dye spreads into a veil. The importance follows. Many early red sources stay tight. Their light concentrates into a small core with a steep brightness gradient. The edge drops quickly into darkness. This physical detail suggests high central density. It also suggests that outer halos may be faint or absent. The primary visual anchor forms. A dark pane of glass holds a single bead of rain. The bead is bright at the centre. A thin halo surrounds it. The halo fades smoothly and then ends. The bead looks simple. The physics behind it can be layered. The second concept is color curvature. Color curvature is how brightness changes across infrared bands. The definition stays brief. 2 analogy sentences follow. Warm clay looks different under candlelight than under morning light. The shift is not one step, it is a gradual curve across shades. The importance follows. A smooth curved spectrum can indicate dust heated by hidden power. A flatter spectrum can indicate different mixtures of stars and gas. In that region, compact red sources often show a broad warm glow rather than sharp features. This can fit a dust reprocessing picture. It can also fit a thick accretion disk picture. A payoff arrives early. The same observed redness can emerge from 2 engines. One engine is intense star formation inside a compact dusty core. The other engine is accretion onto a massive black hole with dust around it. The question then becomes which engine dominates. A main number anchors the scale. Many compact red sources can be only about 1,000 light-years across, like a small island compared to a continent-sized galaxy disk. The comparison keeps it calm. The scale shift follows. 1,000 light-years is huge in ordinary life. It is tiny compared to the cosmic distances that separate the sources. Many such tiny islands appear across a vast early volume. Their abundance turns a curiosity into a population. A payoff arrives again. Population behavior matters more than any single object. If compact red sources are common, then either early stellar cores are denser than expected, or early black hole engines are more widespread than expected. Either option supports the claim that the early universe is brighter. Another visual anchor appears secondary and slow. A field of black sand holds scattered garnet grains. Each grain is deep red. Each grain is small. In dim light, only the red grains stand out. The field seems sprinkled with embers. This is how compact red sources can dominate a deep image. Their contrast makes them easy to count. That ease can bias interpretation. The limit of observation enters with precision. The limit is band-limited inference and blending. With only broad bands, a curved dust spectrum can masquerade as an accretion spectrum. With limited resolution, a compact core and a close companion can blend. The blend looks like one brighter red dot. The limit is also lensing without obvious arcs. Mild magnification can lift faint sources into detection. It can do so without dramatic distortion. That can inflate counts at the bright end. A payoff follows. Recognizing these limits prevents overinterpreting any single color. It shifts attention to consistent patterns across many objects. For example, compactness combined with extreme redness is harder to explain with ordinary older galaxies. It is easier to explain with dense early conditions. Another physical detail grounds the internal structure. A compact red source can show a central peak that is slightly flattened. It can show a shoulder in its brightness profile. That shoulder can indicate a thicker dust layer or an extended warm component. The shoulder can also indicate a second component that is not fully resolved. The shape becomes a clue. A payoff lands softly. Shape is a second language beyond color. A very sharp peak suggests a point-like engine. A smoother peak suggests an extended stellar core. The difference is subtle. The difference is valuable. The section keeps to 2 core ideas and lets consequences unfold. Compactness points to density. Color curvature points to dust or accretion. Together they frame the role of these objects in early brightness. If many are accretion-powered, then early black holes grow fast and contribute to the cosmic light budget. If many are starburst-powered, then early star formation is more intense and more obscured than expected. Both outcomes affect chemical enrichment. Both outcomes can affect reionization timing. Both outcomes can influence how the early cosmic web is traced by light. A scale shift arrives again. The core region that emits most light can be smaller than the host galaxy. That core can be governed by gas dynamics on the scales of light years. Yet the statistical count of such cores informs volumes measured in millions of light years. A small engine leaves a large imprint on cosmological inference. The limit of intuition appears gently. Intuition expects early galaxies to be ragged and diffuse. Intuition expects red color to mean pure distance. Both expectations can fail. Density can rise quickly in the earliest peaks. Dust can redden even in youth if enrichment is rapid. Accretion can add light without adding size. A payoff arrives. When intuition fails, a stable method is to track what changes with wavelength and what stays. A true distance effect shifts features. Dust bends the spectrum smoothly. Lensing distorts shapes. Each effect leaves a distinct fingerprint when enough data exist. The closing transitions without tension. The next section moves to gravitational lensing and natural magnification. It shows how arcs and subtle brightening can mislead counts and also reveal hidden sources. The dark sand field remains. The garnet grains are still. The focus shifts to the invisible mass that can make them seem brighter. A curved arc of light can appear in a deep field like a quiet signature written by invisible mass. Light behaves as if space itself is shaped, and gravitational lensing can brighten and stretch early galaxies without adding any new light. The first concept is lensing. Lensing is gravity bending paths of light. The definition stays short. 2. Analogy sentences follow. A clear glass marble can bend a straight line behind it. The line becomes a curve even though nothing has moved. The importance follows. A foreground mass can act like that marble on cosmic scales. It can magnify a background source. It can also distort shape into arcs and partial rings. A payoff arrives early. If magnification is present, then a galaxy can look brighter than it truly is. That matters for the claim of an overly bright early universe. It does not erase the claim. It reshapes the counts at the bright end. The primary visual anchor forms. A smooth pond reflects moonlight. A shallow ridge under the water bends the reflected stripe. The stripe pinches into a bright crescent. Nearby it widens into dimmer haze. The crescent is not a new light. It is a redistributed reflection. Lensing works in the same calm way. It redistributes light across the image plane. It creates bright curved segments where alignment is favorable. A physical detail sharpens the idea. A lensed arc has a sharp inner edge and a softer outer edge. The brightness can peak along a thin rim. The rim can show small clumps like beads. Those beads are parts of the background source stretched into a line. In stronger cases, a ring-like structure can appear. The ring can be incomplete. It can break into several arcs. The details depend on geometry. The second concept is magnification bias. Magnification bias is lensing, making faint sources detectable. The definition stays brief. 2 analogy sentences follow. A faint star in a window becomes visible when a raindrop acts as a tiny lens. The star was always there. The raindrop only makes it easier to see. The importance follows. In a survey, detections are limited by sensitivity. Lensing can lift a faint early galaxy above that limit. It can do so more often than intuition expects because there are many potential lenses along long sightlines. A payoff arrives again. The brightest rare objects may be overrepresented if a modest magnification is enough to push them into the sample. This can inflate inferred luminosities. It can also inflate the apparent number of extreme early galaxies. Yet lensing cannot create a population from nothing. It can only reshuffle which members are most visible. A main number anchors the effect. A typical strong lensing magnification can be about 10 times like reading small print through a handheld magnifier that makes letters 10 times larger. The comparison stays plain. The scale shift follows. A small mass concentration in a galaxy group can affect light travelling across billions of years. The lens itself can be far smaller than the background distance. The influence extends along the entire light path. A payoff lands softly. This is how a local change in curvature becomes a cosmological correction. Another visual anchor appears secondary and slow. A thin sheet of ice covers a stream. Beneath it, a stone deflects flow. The surface pattern above the stone shows a curved wake. The wake reveals the stone without touching it. Lensing does the same. The arc reveals the distribution of mass. It reveals a smooth component and a clumpy component. The arc can show small kinks. The kinks can signal substructure. Yet the section keeps calm and selective. The focus is not mapping every lens. The focus is understanding how lensing affects the early galaxy census. The limit of observation now enters with precision. The limit is recognizing lensing when distortion is subtle. Not every magnified source forms an obvious arc. Mild magnification can leave a source only slightly stretched. If resolution is finite, that stretch can be lost in the point spread blur. The inference then relies on statistical excess near known lenses. It relies on modelling based on limited information. Another limit is mass model degeneracy. Different mass distributions can produce similar arcs. Without additional constraints, magnification can be uncertain. That uncertainty feeds directly into luminosity estimates. A payoff follows. Because magnification is uncertain, safe claims about extreme brightness need ranges rather than single values. This does not weaken the story. It makes the story steep. Another physical detail grounds how arcs form. The strongest arcs appear near a critical curve. A critical curve is where magnification peaks. The definition is brief and simple. 2 analogy sentences follow. A soap film can show a bright band where thickness changes rapidly. The band marks a boundary. The boundary concentrates reflected light. The importance follows. Near a critical curve, small background structure becomes elongated. Brightness rises along a narrow band. That is why arcs look like thin crescents with bright rims. A payoff lands again. Seeing an arc is not only a warning about magnification, it is an opportunity. The arc acts like a natural telescope. It reveals structure inside the background galaxy that would otherwise be below resolution. It can reveal clumps. It can reveal gradients. It can reveal a compact core and a faint skirt. This helps address earlier limits about blending and surface brightness. The section shifts into a gentle scale shift. The clumps in an arc can correspond to star-forming regions. Those regions are small compared to the host galaxy, yet they are stretched into features that span many pixels in an image. A local patch becomes visible across cosmic distance. The lens translates small structure into accessible structure. Another visual anchor arrives. A thin strip of sunlight passes through rippled glass. The strip breaks into bright and dim bands. Each band is a distorted view of the same light source. Lensing similarly creates multiple images. It can create pairs, it can create triples, it can create a faint counter-image. The counter-image can be hidden in glare or noise. The limit is specific. Detecting faint counter-images is hard at extreme depth. Without them, model constraints weaken. A payoff follows. Even partial information can still constrain plausible magnification. It can still bound intrinsic brightness. Bounds are enough to test whether early galaxies are truly too bright. The arc of the script stays steady. The next section moves from lensing to the larger structure that lensing reveals. It shifts from individual distortions to the cosmic web and early clustering. The transition is calm, the pond surface remains. The crescent of reflected light fades. The underlying ridge is still implied, shaping the next view. A scattered set of faint points can outline a pattern long before any lines are drawn. In that region, early clustering suggests the cosmic web forms faster than expected, and helps explain why the young universe looks denser and brighter. The first concept is the cosmic web. The cosmic web is a network of filaments and voids. The definition stays short. 2 analogy sentences follow. Dew gathers along strands of a spider web at dawn. The empty gaps between strands remain nearly invisible. The importance follows. Galaxies form and light up along filaments. Voids stay dark and quiet. Even in a small patch of sky, the distribution can hint at the web. The primary visual anchor forms. A thin sheet of frost spreads across a window. Bright crystalline branches grow first. Dark, clear patches remain between them. The branches meet and fork. The pattern looks inevitable. In early surveys, luminous sources appear in clumps and chains. The chains are not drawn. They are implied by where sources prefer to sit. A payoff arrives early. If early galaxies already cluster, then gravity has already amplified small initial ripples into significant contrast. This makes a brighter early universe less surprising. Dense peaks light up first. The second concept is bias. Bias is galaxies forming in denser regions first. The definition stays brief. 2 analogy sentences follow. Seeds sprout first in the dampest soil. Dry soil stays bare even when the same rain falls. The importance follows. The earliest galaxies are not a random sample of space. They are drawn from the highest density peaks. Those peaks are more common in some models than others. If more peaks exist, more early galaxies appear. If peaks are more efficient at forming stars, early light increases. A main number anchors the scale. Filaments can span about 100 million light-years like a single thread stretching across a continent-sized map. The comparison holds the vastness gently. The scale shift follows. A tiny density ripple in the early universe grows into a filament longer than any cluster. That filament then hosts many galaxies. Each galaxy can be only a few thousand light-years across. Small islands of light trace a structure that is millions of times larger. A payoff arrives again. Brightness excess can be partly a geometric effect. If galaxies crowd into filaments, the sky patch looks crowded. The same number of galaxies spread uniformly would look sparse. Clustering raises local surface density on the sky. It also increases lensing probability because mass is concentrated. This links back to previous sections without strain. Another visual anchor appears secondary and slow. A shallow stream flows over pebbles. Water finds channels. The channels deepen. The banks stay higher and drier. The flow pattern appears stable even though each droplet moves on. The cosmic web is similar. Matter flows along gradients. Dense nodes grow. Voids drain. The shape emerges from gravity acting over time. A physical detail sharpens the web. In filamentary regions, density gradients can be steep. The gradient can pull gas into elongated structures. Galaxies can show slight elongation aligned with local flow. Groups can appear as beads along a faint bridge. The bridge may be too faint to see directly, yet the spacing of beads can imply it. A payoff lands softly. Even without seeing the filament glow, the arrangement of luminous nodes can reveal it. The section now holds its limit of observation. The limit is cosmic variance and projection. In a small observed area, a rare overdense region can dominate counts. Another region might be underdense and look quiet. The difference can be chance. The limit is also line of sight confusion. 2 galaxies at different distances can project near each other. They can mimic a physical group. To distinguish true clustering from projection distance, estimates must be accurate. Spectroscopic confirmation helps. Yet spectra are hard for faint sources. The result is uncertainty. A payoff follows. Because of these limits, clustering is tested statistically across many independent fields. Repetition reduces the impact of any one overdense patch. Another limit is resolution. If many small sources blend, the apparent clustering increases. Blending can create a false bright node. It can also erase faint bridges. This is why deblending methods matter. Yet deblending is not perfect. It can split one object into 2. It can merge 2 into 1. The uncertainty again pushes toward ranges rather than absolutes. A payoff arrives again. Even with uncertainty, the broad conclusion can stand if multiple fields show similar early crowding. The web then becomes a plausible framework for the brightness claim. The section keeps the tone gentle and the concepts limited. Cosmic web provides the scaffold. Bias explains why early galaxies are not evenly spread. The rest of the reasoning follows naturally. If bias is strong, early light comes from rare peaks. That can produce surprisingly bright objects. It can also produce early massive engines because dense peaks supply fuel. The web can feed gas along filaments. Gas flows toward nodes. Nodes build deep potential wells. Deep wells can host compact disks and dust. Another physical detail grounds the inflow. Gas can form streams that are narrow compared to the node size. The streams can strike a central region and build a rotating disk. The disk can show a radial gradient in temperature. Dust can settle into a thicker outer layer. The layered structure then emits a smooth infrared continuum. A payoff lands. The Webb is not only a distribution of points, it is a supply network for this early bright universe. Yet the section avoids personification. The Webb is not active by intention, it is a consequence of gravity and expansion. The scale shift returns for a calm closing. The same equations that describe a small ripple also describe a filament. The same physics that shapes a droplet channel can shape a matter flow. Small beginnings become large structure over long time. The next section moves from structure to expansion itself. It brings in the Hubble tension as a mismatch between two expansion measures. It frames the tension with the calm patience of a measured discrepancy. The frost branches remain on the window. The clear gaps remain. The view slowly zooms outward to the expansion that stretches everything between them. A small mismatch in expansion can feel like a gentle offset between two steady clocks. In that region, the Hubble tension is the persistent difference between early universe and late universe. Expansion estimates and early brightness can nudge the interpretation of both. The first concept is the Hubble constant. The Hubble constant is the present rate of cosmic expansion. The definition stays short. Two analogy sentences follow. A loaf of rising bread expands everywhere at once. A single raisin sees other raisins drift away faster when they are farther. The importance follows. Expansion sets the distance scale of the universe. If the scale shifts, then inferred sizes ages and densities shift with it. A payoff arrives early. The tension matters because it suggests either hidden measurement bias or missing physics. The primary visual anchor forms. Two pendulums hang in a quiet room. Their swings are almost synchronized. Over time, one pendulum slowly drifts ahead. The drift is small. It is persistent. The room stays calm. The mismatch still demands explanation. The Hubble tension has that same feeling. Two methods measure expansion. One method uses early universe imprints. Another uses late universe distance ladders. Their answers are close but not identical. A main number anchors the difference. The mismatch is around 10%, like two rulers that disagree by one small segment across a 10-segment span. The comparison keeps the scale simple. The scale shift follows. A 10% change in expansion rate can alter inferred distances across billions of light years. It can also change the age inferred from the expansion history. A small offset today echoes across cosmic time. The section moves through checkpoints. First, the early universe method relies on a standard scale set by sound waves in the primordial plasma. That scale becomes a ruler printed into later large-scale patterns. The imprint is not described with technical symbols. It is a physical memory of pressure waves. Second, the late universe method builds distances step by step. It uses objects with known brightness behavior. Those objects are calibrated locally. Then they are extended outward. A payoff arrives again. Both methods are internally consistent. The disagreement lies between them. This is why it is called tension rather than error. The section holds only a few concepts. Hubble constant and two clocks are the frame. The rest is careful linkage. The early brightness results can influence the tension in two ways. One way is through selection and bias in distance indicators. If the early galaxies appear brighter or more numerous than expected, then assumptions about dust crowding and blending become more important. Those same issues can affect the calibration of distance indicators at moderate redshift. If light from neighbors blends into a standard candle host as the host can look brighter, the inferred distance can shift. Another payoff arrives. A small systematic brightness shift can propagate into the inferred expansion rate. The other way is through cosmological parameters. Early brightness and early structure growth depend on how matter clumps over time. Clumping depends on expansion history. If the early universe expands or cools in a slightly different way than assumed, then structure growth changes. This can influence the interpretation of early imprints and late clustering. A physical detail grounds the measurement challenge. In crowded fields, brightness profiles overlap. The combined light creates a smooth pedestal. The pedestal raises the background. A true point source then sits on a higher base. This changes measured flux. The edge of the point spread blur sets how much overlap occurs. The blur has wings. The wings extend farther than intuition expects. A payoff follows. Recognizing this physical overlap helps explain why meticulous corrections are essential for distance ladders. It also explains why improvements in resolution and analysis can shift inferred values. The limit of observation now enters with precision. The limit is systematic uncertainty rather than random noise. Random noise averages down with more data. Systematic bias can persist. It can come from calibration drift. It can come from dust corrections that depend on environment. It can come from selection effects where only the brightest objects are used. It can also come from modelling assumptions in the early universe method. For example, the standard ruler size depends on early physical conditions. If those conditions are slightly different, the ruler changes. Another payoff arrives. The tension could be reduced by revising the ruler or revising the ladder. The challenge is that both sides have many cross-checks. The section keeps calm by framing the tension as a diagnostic tool. It is not a crisis, it is a probe. The next checkpoint focuses on how early brightness intersects with a specific ladder issue. Early galaxies being denser means more crowding and more background light in deep fields. Crowding can bias photometry. Photometry is measuring brightness in images. The definition stays short. Two analogy sentences follow. A single candle is easy to measure in a dark room. Many candles together make individual flames harder to separate. The importance follows. When separation is hard, brightness can be misassigned. That misassignment affects distance estimates. Another visual anchor appears secondary and slow, a pattern of faint fireflies in tall grass pulses. Some pulses overlap. A few appear brighter when two align. The eye cannot always tell which insect makes which glow. This is blending. In astronomy, blending can raise measured brightness and reduce inferred distance. Reduced distance can raise inferred expansion rate. A payoff lands softly. This provides a pathway for some of the tension without invoking new physics. Yet the pathway must be tested. Not all ladders are equally sensitive. Not all fields are equally crowded. The section returns to early universe constraints. Early imprints are inferred from patterns on the sky. Those patterns depend on the sound horizon scale and the matter content. If early galaxies suggest faster structure growth that can point to small adjustments in parameters, yet adjustments must fit many observations at once. The limit of intuition appears gently. It is tempting to treat the tension as one knob to turn. In reality, many knobs are linked. Changing one can spoil agreement elsewhere. That is why the tension persists. It survives many attempts at simple fixes. Another payoff arrives. Persistence means the discrepancy is real at the level of analysis, even if the cause remains uncertain. The closing transitions without suspense. The next section explores how early brightness ties to the growth rate of structure and to the background glow of the early universe. It keeps the same gentle clock imagery. The pendulums continue. Their drift remains small. Their steady motion invites a careful listen rather than a rush to resolve. A faint glow can be more informative than a bright point when it fills the gaps between galaxies. At this distance, the early universe can look brighter because many small sources add light together, and that combined light influences how structures grow and how expansion is inferred. The first concept is the extragalactic background light. Extragalactic background light is the sum of light from all galaxies. The definition stays short. Two analogy sentences follow. A city seen from far away becomes a soft dome of light. Individual lamps vanish. The sky still brightens. The importance follows. A deep field is not only a set of dots, it is also a faint flaw of accumulated photons. That flaw carries information about how much star formation and accretion occur over time. The primary visual anchor forms. A valley at night holds a layer of mist. A few distant lights pierce it. The mist itself becomes gently luminous. The glow has a smooth gradient. It is brighter near the valley floor. It fades toward the ridgelines. In cosmic terms, the glow is the background light. The dots are galaxies. A payoff arrives early. If many ultra-early galaxies exist below detection, the background can rise even when individual sources remain unseen. This helps reconcile a brighter early universe with limited direct counts. The second concept is rionization. Rionization is when neutral gas becomes ionized by light. The definition stays brief. 2 analogy sentences follow. Morning light turns a foggy field from grey to clear. The change is gradual and patchy. The importance follows. The early background light is not only warmth and colour, it changes the state of gas between galaxies. Ionized gas is more transparent to some wavelengths. It also changes how gas cools and collapses. A physical detail grounds the process. Ionization fronts create sharp boundaries. A boundary separates neutral regions from ionized bubbles. The bubble edge can be thin, the interior can be more transparent. The exterior can sucker and absorb more strongly. These bubbles can overlap. Overlap turns patchwork into a more uniform state. A payoff arrives again. If early galaxies are more numerous or more luminous, bubbles form earlier, and overlap does near. That shifts the timeline of reionization. It also changes the visibility of certain spectral features. A main number anchors the epoch. Reionization mostly completes by about 1 billion years after the beginning, like finishing a long dawn where the last shadows fade near the end. The comparison stays gentle. The scale shift follows. A 1 billion year interval is vast, yet the ionization boundary around a single galaxy can expand on timescales much shorter than that. Local changes accumulate into a global phase change. Another visual anchor appears secondary and slow. A lake in early morning shows patches where ice turns to water. The boundary is jagged. The dark water absorbs more light. The bright ice reflects. Over time, the patches merge. Reionization is similar in geometry. Bubbles are the water. Neutral regions are the ice. The shape evolves as sources turn on and off. A payoff follows. The patchiness means that any single line of sight can be misleading. 2 regions at the same cosmic time can look different. One can be clearer. One can be more absorbed. This variability affects the interpretation of early galaxy spectra. It also affects inferred star formation rates. The limit of observation enters with precision. The limit is separating faint background light from the instrument background and foreground contamination. Even in an ideal deep field, the measured flaw includes many components. Small errors in subtraction can mimic a cosmic glow. Another limit is that much background light comes from sources below the detection threshold. Their properties must be inferred statistically. That inference depends on assumed distributions of galaxy brightness and dust. A payoff arrives. Because of these limits, background light is often constrained by upper and lower bounds. Those bounds still inform early galaxy models. They still test whether unseen populations are required. The section keeps only 2 core concepts and lets them connect. Background light is the integrated output. Reionization is the gas response. Together they link early brightness to cosmic state. If early brightness is high, reionization proceeds efficiently. If reionization proceeds efficiently, then the medium becomes more transparent. Greater transparency can make more galaxies visible in certain bands. This creates a feedback in observation rather than in physics. A clearer medium reveals more sources. More sources raise the inferred brightness. A payoff lands softly. Recognizing this observational loop helps keep claims stable. It encourages modeling that includes both source populations and the state of the medium. A physical detail returns to anchor the photon budget. Ionizing photons can be absorbed by dense gas near galaxies. Escape fraction is the fraction of ionizing photons that leave. the definition stays short. Two analogy sentences follow. Steam in a pot escapes through a loose lid more easily. A tight lid keeps most steam inside. The importance follows. Even a luminous galaxy contributes less to ionization if photons do not escape. This means early brightness in infrared is not a direct measure of ionizing power. Dust can also absorb. Gas can also absorb. Geometry matters, a payoff arrives. This explains why early galaxies can be bright yet still allow ionization to remain extended and patchy. It also explains why constraints remain uncertain. Escape fraction is hard to measure directly at extreme distance. It is inferred from indirect features. The limit of observation appears again. The limit is that direct measurement of ionizing photons is blocked by absorption along the line of sight at high redshift. That forces reliance on proxies. Proxies can disagree. Proxies can depend on dust and age. A calm payoff follows. Multiple proxies across many galaxies can still constrain typical escape. The average can emerge even when individuals are uncertain. The scale shift returns for a quiet closing. A single photon leaves a star in a compact galaxy. It crosses a local bubble. It crosses filaments and voids. It arrives after billions of years and adds to a faint background flaw. Many such photons build a glow that changes the medium. The next section moves from this integrated glow to the direct count of galaxies and the implied star formation history. It remains calm and bounded. The valley mist stays luminous. The individual lights remain small. The soft dome of glow becomes the guide into the next step. A single faint curve in the infrared can act like a quiet diary of how quickly stars are being made. In that region, the star formation history inferred from early galaxies can rise faster than expected, and the shape of that rise affects both brightness claims and models of structure growth. The first concept is star formation rate density. Star formation rate density is stars formed per volume per time. The definition stays short. 2 analogy sentences follow. A bakery can be judged by loaves per hour. A whole city can be judged by loaves per hour per neighborhood. The importance follows. Star formation rate density is a global measure. It turns many individual galaxies into one smooth history curve. A payoff arrives early. If the early universe is denser and brighter, the curve may start higher and climb earlier than predicted. That suggests either more galaxies, more efficient star formation, or both. The primary visual anchor forms. A long shoreline receives incoming waves. Each wave leaves a thin, wet line on sand. The lines stack and fade. The shoreline records the rhythm of the sea without keeping any single wave. A star formation history curve is similar. Each galaxy is one wave. The combined record is a set of overlapping traces that form a smooth slope. A physical detail grounds the observation. Early galaxies often show steep ultraviolet brightness gradients. The core is bright, the outer regions fade quickly. This implies concentrated young stars or concentrated unobscured light. Yet dust can hide star formation and shift light into infrared. The section stays calm by separating visible and hidden contributions. A key checkpoint appears. Observed ultraviolet light traces young stars that are not heavily obscured. Infrared light traces dust warmed by starlight or other power sources. Converting either into a star formation rate requires assumptions. Those assumptions include the age distribution of stars, they include dust properties, they include how much light escapes. A payoff arrives. Because assumptions matter, different methods can yield different early curves. Comparing methods is a way to diagnose hidden bias. The main number anchors a timeline point. The curve begins to rise sharply within about 500 million years after the beginning, like a garden that shows a sudden surge of green after the first long rains. The comparison stays gentle. The scale shift follows. 500 million years is longer than any recorded history. It is still early compared to the age of the universe. In that short cosmic interval, small halos gather gas. Gas cools, stars ignite, metallicity rises, dust begins to form. Another visual anchor appears secondary and slow. A hillside after a rain shows rivulets. At first, only a few channels run. Soon many channels appear. They merge into a wider flow. The hillside looks more active without any single channel being dramatic. This is how star formation rate density can rise. Many modest galaxies can contribute. A few bright galaxies can also contribute. The balance matters. This leads to the second concept. The second concept is the luminosity function. Luminosity function is the number of galaxies by brightness. The definition stays brief. 2 analogy sentences follow. A jar of pebbles has many small stones and few large stones. The total weight depends on both counts and sizes. The importance follows. If there are many faint galaxies, the integrated star formation can be high, even if few bright galaxies exist. If the bright end is enhanced, the history can look dominated by rare objects. This directly touches the brightness claim. A payoff arrives. Measuring the slope of the faint population is central. A steep faint slope means unseen galaxies contribute strongly. A shallow faint slope means most light comes from those already detected. Both scenarios can fit some data. Distinguishing them requires depth and careful completeness corrections. A physical detail sharpens what completeness means. At the detection limit, only the peaks of bright regions are seen. Low surface brightness outskirts are missed. The edge of a galaxy can fall below background. The measured flux then underestimates true flux. This bias grows for diffuse objects. It also grows when background varies. Another payoff arrives. Underestimated flux can make galaxies seem smaller and less massive. Correcting it can raise inferred star formation. Yet overcorrecting can create false excess. The limit of observation enters with precision. The limit is selection and dust degeneracy. Faint galaxies are hard to detect. Dusty galaxies can be faint in ultraviolet. They can still be actively forming stars. If dust corrections are uncertain, then inferred star formation rate density can be uncertain. Another limit is contamination by non-stellar power. Some infrared emission can come from accretion rather than stars. If that is misattributed to star formation, the early curve rises artificially. The limit is not only instrument sensitivity, it is model separation. A payoff follows. Recognizing these limits motivates cross-checks using spectral shapes and population consistency. If the inferred star formation implies too much metal enrichment too quickly, that can flag an overestimate. If it implies too little ionizing output, that can flag an underestimate. Constraints from ionization provide another check. Constraints from background light provide another check. The section keeps its gentle rhythm by turning each check into a small unlock. The galaxy count curve does not stand alone. It must agree with the state of the intergalactic medium. It must agree with the observed clustering. It must agree with background glow limits. Agreement narrows plausible histories. A scale shift arrives again. A single galaxy may form stars in a compact core only a few thousand light-years wide. That core can change it on timescales of millions of years. Yet the global star formation history is averaged over volumes spanning millions of light-years. It is averaged over intervals spanning hundreds of millions of years. Local bursts blur into a smooth curve. Another payoff arrives. This explains why a bright early universe can coexist with calm averaged histories. The curve can be smooth even if individual galaxies flicker. The shoreline keeps stacking wet lines. None of the lines is singled out. The closing transitions softly. The next section turns to what early brightness and early star formation imply for matter, content and energy content. It considers how model parameters respond. It keeps the mismatch and the corrections gentle. The shoreline remains. The waves continue. The record becomes the guide into the next step. A model can feel sturdy until a new weight is placed on a corner that has never been tested. In that region, a denser and brighter early universe shifts the balance of cosmological parameters and reveals where the standard model is flexible or rigid. The first concept is matter density. Matter density is the amount of matter per cosmic volume. The definition stays short. 2 analogy sentences follow. A soup with more beans thickens the whole pot. A thinner soup lets ingredients drift more freely. The importance follows. Matter density controls how strongly gravity can grow structure. It also influences how the expansion slows in the early universe. A payoff arrives early if early galaxies and early clustering appear too strong. One response is to raise effective matter density or its influence. Yet any change must remain consistent with other measurements. The primary visual anchor forms. A wide sheet is stretched across a frame. Small beads rest on it. The sheet is nearly flat. A few heavier beads create deeper dimples. Nearby beads roll gently towards the dimples. The dimples represent gravitational wells. The sheet represents the expanding background. The bead motion stays calm. The picture still explains. A physical detail grounds the analogy. The dimples have curvature gradients. Steeper gradients pull more strongly. Shallow gradients barely guide motion. In cosmic structure, the gradient is the gravitational potential. The depth depends on mass distribution. The next checkpoint connects brightness to mass. Brightness in early galaxies implies star formation and accretion. Both require gas inflow. Gas inflow is easier in deeper wells. Deeper wells are more common if density fluctuations grow efficiently. Growth efficiency depends on expansion rate and matter content. Another payoff arrives. This explains why early brightness, early clustering, and the Hubble tension can be related through the shared background expansion history. The second concept is dark energy. Dark energy is the component that accelerates expansion at late times. The definition stays short. 2 analogy sentences follow. A gentle tailwind can make a boat drift faster without adding oars. The same river current can still carry it, but the drift changes. The importance follows. Dark energy affects distances at moderate and low redshift. It also affects how late-time structure grows. If late-time expansion is faster, then growth slows. That changes the mapping between early seeds and late structures. A payoff arrives. Adjusting dark energy behavior could ease the Hubble tension without altering early physics too much. Yet such adjustments can conflict with other constraints. The section keeps the concepts limited and uses careful transitions. First, the standard model assumes a simple evolution. Matter dominates early. Dark energy dominates late. In between both matter and dark energy matter. If early brightness suggests faster early growth, then either seeds are higher growth, is stronger, or selection is biased. Seeds relate to initial fluctuations. Growth relates to matter content and expansion history. Selection relates to observation and analysis. The section stays calm by holding all 3 as possibilities. The main number anchors the late-time effect scale. Dark energy dominance becomes important within about the last 5 billion years, like a long walk where the final stretch has a slight downhill slope that changes pace. The comparison stays gentle. The scale shift follows. 5 billion years is immense. The acceleration it causes is subtle at any moment. Over long time, it reshapes distance relations. It changes how far objects appear for a given redshift. It also changes the age inferred for a given expansion curve. Another visual anchor appears secondary and slow. A river splits into 2 channels around a sandbar. One channel is deeper, the other is wider. Both carry water to the same downstream reach. The choice of channel changes travel time. In cosmology, different parameter combinations can yield similar observable distances over some range. This is degeneracy. A payoff arrives. Degeneracy means multiple parameter tweaks can mimic each other in limited datasets. Breaking degeneracy requires multiple independent probes. The limit of observation enters with precision. The limit is that many probes share underlying assumptions about standard candles, standard rulers, and astrophysical modeling. Even when probes are independent in method, they can depend on shared calibrations or shared priors. Another limit is that extreme redshift observations rely on faint signals. Faint signals require complex processing. Processing choices can shift inferred brightness and counts. The limit is not only noise, it is modelling dependence. A payoff follows. Because of these limits, parameter shifts are tested by consistency across many scales and epochs. If a change helps early brightness but worsens late clustering, it is suspect. If it helps the Hubble tension but breaks the background light constraints, it is suspect. Consistency acts like a quiet filter. The section returns to physical detail in the parameter space. Increasing matter density deepens the dimples on the sheet. It increases the rate at which small perturbations grow. It can also shift the time when structures become non-linear. Non-linear means growth becomes complex and not proportional. The definition stays short. 2. Analogy sentences follow. A small wrinkle in fabric can grow into a fold. Once it folds, the shape no longer scales simply. The importance follows. Early nonlinear growth could help explain early massive objects, yet it would also affect later statistics. Another payoff arrives. This reveals why early brightness cannot be interpreted in isolation. It must fit with later galaxy clustering and lensing constraints. Adjusting dark energy instead changes the sheet tension at late times. It alters how quickly the sheet stretches. It can slow growth later while leaving early growth similar. That can help match late structure while allowing early structure. Yet if dark energy changes too early, it impacts the standard ruler calibration. This loops back to the Hubble tension. Another payoff arrives. The model is a connected fabric. Pulling one corner moves other corners. The section maintains calm by turning this into a stable picture rather than conflict. The stretched sheet and beads remain. The dimples deepen or shallow slightly. The bead motion changes subtly. No dramatic snap occurs. The scale shift returns once more. A local change in parameter can adjust distances across billions of light years. It can also adjust growth across billions of years. Yet the change can be described as a few % here or there. This gentle mismatch is why the problem persists. It is hard to distinguish tiny shifts from tiny biases. The closing transitions softly. The next section resolves the arc by stepping back into a quiet overview. It gathers the denser, brighter early universe, the rapid growth of massive objects, and the expansion mismatch into one calm picture. The sheet remains stretched. The beads settle. The model is not broken, it is being gently tested. A faint, even glow still fills space like a hush that never quite leaves. It is the oldest light that can travel freely released when the young universe first becomes transparent. This glow is called the cosmic microwave background. It is light set loose when hot matter cools enough for photons to slip through. In that moment, space stops acting like fog. It starts acting like clear air. The story begins close at the level of a single photon. It bounces among charged particles in a dense plasma. The path is restless and short. It is a walk through crowding, not a flight through emptiness. Then the crowd thins. Electrons bind to nuclei. Free charges vanish in bulk. Light no longer ricochets at every step. The first payoff arrives quietly. Transparency is not a poetic word here. It is a physical switch that turns scattering off. A surface forms not made of matter. It is a boundary in time. It is the last scattering surface. Last scattering surface means the final veil light passes through. After that, boundary photons travel almost straight for billions of years. The glow is not bright in any dramatic way. It is gentle, nearly uniform. Yet it carries a subtle texture. There are warmer and cooler patches. The pattern is soft and granular. It resembles frost on a windowpane at dawn. The frost is the anchor of the scene. Pale speckles spread across a quiet sheet. Some grains cluster into faint islands. Some areas look slightly smoother. The eyes drift without effort. The second payoff sits inside those speckles. Each patch is not a stain on glass. It is a memory of density ripples in the early plasma. A density ripple is a small region that is slightly heavier. Heavier regions pull harder with gravity. In that region, matter compresses the plasma. Compression heats it a little. Light leaving that region carries a slightly higher energy. Nearby other regions expand and cool. Their photons emerge a little softer. The texture is a fossil of pressure waves. Those waves are like gentle rings in a pond, except the pond is the entire universe. A scale shift happens without strain. One can imagine a ripple the size of a room, then the same logic stretches outward. The ripple pattern repeats across distances so vast that a single patch spans many millions of light years. The speckles look small because the canvas is enormous. The third payoff is that the pattern is not random noise. It has preferred sizes. It has a calm geometry. Sound waves in the plasma travel for a limited time. They can only move so far before transparency arrives. That maximum travel distance sets a characteristic scale. It is a standard ruler written in heat. It lets the cosmos be measured without touching it. Here one number can enter without fuss. The light has been travelling for about 14 billion years, like a calendar with pages turning every day until the stack reaches beyond any skyline. The number is not used for drama, it is used to settle perspective. A photon leaves a warm patch when the universe is young and compact. It crosses expanding space while the cosmos grows vast and dilute. The wave of light stretches along the way. Expansion lengthens its wavelength. That stretching cools the glow into microwaves. Light behaves as a memory foam keeping shape while slowly widening. The metaphor holds in one way only. The wavelength grows. The photon count does not need to grow. The energy per photon drops. The afterglow cools into a long, soft whisper of radiation. Another visual anchor arrives within the same frost scene. The boundary between warm and cool patches is not sharp. It has gradients. The edges blur. That blur has a cause. Photons do not all escape at the exact same instant. Some scatter a little longer. Some last collisions happen slightly earlier. The last scattering surface has thickness. It is not an infinitely thin shell. That thickness smooths the smallest features. It is like frost that softens at the edges, where glass holds a bit more warmth. The fourth payoff is that the blur itself carries information. It marks the limit of fine detail. It sets a ceiling on how small a ripple can be seen in this oldest light. Here the limits of observation enter gently and clearly. No direct image can show anything earlier than the last scattering surface. Before transparency, the universe is opaque to light. Photons cannot stream freely through the plasma. They keep scattering. Any earlier pattern is erased into uniformity by repeated collisions. This is not a failure of patience. It is a physical barrier. It is a limit imposed by scattering and by finite thickness. Another limit follows. Even after transparency, the glow is seen from a single vantage point in a single universe. The largest patterns are few in number. They cannot be averaged away. This is a sampling limit. It is not a flaw in mathematics. It is a consequence of having only one sky. A signal would reveal large-scale waves only in broad strokes. The fifth payoff is that limits do not erase meaning. They shape what can be asked. The cosmic microwave background answers some questions with clarity. It reveals how smooth the early universe is, it reveals the scale of its ripples, it reveals how expansion sets the stage, but it cannot show the first sparks directly. It cannot display the instant when the very first stars ignite. That era comes later when matter clumps enough for collapse. The afterglow is earlier than stars. It is earlier than galaxies. It is earlier than any structure that shines on its own. Yet the afterglow already contains the seeds. The warm speckle is a slightly denser place. Over time, gravity amplifies it. A shallow dip becomes a deeper valley. Gas flows inward. Dark matter shapes the scaffold. The sixth payoff arrives as a quiet chain of cause and effect. The same tiny unevenness that makes a warm patch also makes a future filament. The same cool patch marks a future void. The cosmic web is not drawn later from scratch. It grows from the faint blueprint. Another scale shift completes the journey. The view returns to the photon again. It begins in a crowded plasma moving in tiny steps. It ends in near vacuum crossing billions of light years without a collision. In between, the universe expands, it cools, changes phase from opaque to clear. The frost pattern glow remains as an all-sky background. It does not point to a single object, it is not a spotlight, it is a backlight behind everything else. The final visual is simple. A dark field holds a thin, even mist. The mist has speckles and gentle gradients. It is steady. It is older than any star. From this calm afterglow, the next drift is natural. Matter follows the blueprint slowly. Density ripples become filaments and knots. Light from later eras begins to appear and the long growth of structure takes over.